Welcome to lecture 7. We're sort of at the midway point of the lecture, and to celebrate that, we'll talk about some fancy recurrent neural networks now for one of the hardest tasks in NLP, namely machine translation. So first we'll wrap up briefly in 3 or 4 slides the bidirectional and deep standard recurrent neural networks for opinion labeling. And then we'll start and give a ridiculously short introduction on machine translation and sort of traditional / currently used machine translation systems. That will not do machine translation full justice. We could literally, and there are classes that talk about machine translation for an entire quarter or semester, but we'll focus on deep learning. I just want to give you some sense of what has been done before for some elements, some aspects of the large MT systems that are currently being used that you're probably using if you use Google Translate or other translation services. Machine translation is such a hard task that it motivated a couple of interesting new types of recurrent neural networks, namely gated recurrent units that are very recent and also are part of what's bringing back long short-term memories by Hochreiter and Schmidhuber that are quite a long time ago, or have been published quite a long time ago in our field, sort of what we call deep learning, which we just recently in 2006 or so really started. It seems an ancient, it's from ancient times, but in the grand scheme of academic fields, it's still actually also quite recent. So today will be quite an advanced lecture. We'll have sort of cutting edge blast from the past in the sense that some of these models that are actually simpler and make sense to sort of talk about first to get you a sense of what's going on with gates are actually very recent, just from last year, whereas the LSTMs or long short-term memories are very old. Don't worry if you cannot follow everything we covered today. You should be able to, in theory, if you understood everything so far. It is just, again, putting all these Lego pieces together in various new ways. There's one tiny new Lego piece, these gates, but really that just means multiplication, element-wise multiplication. It is an advanced lecture, so mostly I want you to gain some intuition and encourage some exploration on your own. We can't really derive all the gory details of these models, and really what you should realize at this point is you'll have to somehow modularize your equations. You have to understand what comes into a layer and what comes out of a layer, and everything else will kind of just be put together as you do in forward propagation, which we'll cover mostly today. So don't worry, we'll not ask you to actually derive all the gradients of these models we'll cover today, but in theory, you should be able to. All right, before we get started, are there any organizational questions? Problem set, questions? All right. Cool. So let's get started with the model we ended with last time, which is the deep bidirectional recurrent neural network, which wasn't invented by Ozan Irzar and Claire Cardi, but they used it for labeling opinionated expressions. And again, here we have our input vectors x, and we piped them through these deep networks, but now we did that both from the left to right and from the right to the left, and then we connected all these things to one another, one layer at a time. So the data set is actually an interesting one. It's called the MPUA data set that was introduced by Wiebe in 2005. It basically only has 500 or so news articles, but there are 11,000 or so sentences in that data set, and basically they labeled every single phrase for whether it's these kinds of opinionated expressions or not. And I wanted to make sure you all know the F1 metric. I think several of you had raised your hand when I asked last time, but it's a pretty important metric, and you probably will want to use it in your project, so I just want to make sure we define it here. Basically, it's just a sort of mean of precision and recall. The precision being, you have your true positives, so you have some kind of label for a certain word, for instance, and you actually assign the correct at test time. Your model assigns the correct label to that word. So you have your true positives. You divide that by the sum over the true positives plus the false positives. So you say, for instance, this is a location, but it's not really a location. it's something else. So those are your false positives. And then your recall is, again, your true positives divided by true positives, but plus your false negatives. So you incorrectly said something was not what you thought it was. And then you basically get this nice F1 metric, which now also goes from 0 to 1. And basically, the main result here of that evaluation is that as you add more layers, things get better up until a certain number of layers. So here again, these layers are basically not the feed-forward time, right? That just depends on your sequence, but how deep the model is. Yes? What if you have multiple classes? That's a great question. You can actually compute precision recall for each class. Right? This is quite a binary setting. You can always say, this was a true positive in terms of this being a location or in terms of this being a person and so on. And then you can actually average your F1 scores to get the overall one. So basically, on two different data sets, this model does best when you have 3 layers, and then they also compare with different numbers of parameters, and actually the larger the layers are, the better also. However, that the message there is a lot less clear once you go to higher layers and the model has a lot higher variance. And this is something we often observe. After adding a certain number of layers, there's only so well you can do, and then the model starts to overfit too much on your training data. All right, so let's start with machine translation. It's a really exciting task. Basically, all methods, both traditional or currently used, and in some sense our deep learning ones, are statistical, and they're based on parallel corpora. So what is a parallel corpus? It is basically a large corpus where you have aligned or at least somewhat aligned sentences and paragraphs. So if you take, for instance, all the notes from the European Parliament, and they're written in all the languages of the European Union, and now you have an English sentence, and you have a French sentence, and then you have an Italian sentence, and a German sentence, and so on. Usually we only look at one language pair. So we just translate from one language to another. And in some cases, it's not just on the sentence level, but only on the paragraph level. So you say this paragraph is, in English, what this paragraph is in French. And of course, certain complexities arise the larger sort of units you only have in parallel. The first parallel corpus is actually an interesting story. Is the Rosetta Stone, which allowed us to understand ancient Egyptian hieroglyphs, demotic script, and thanks to us still knowing ancient Greek. So this is actually in some ways the very first parallel corpus that was used for translation, not machine translation, but general translation. And so one thing I'll try to basically bring across to you is how complex these currently used, I call them traditional, they're not really traditional in the sense that they're not being used anymore, they're still currently being used, but basically the main message is that they're very complex. So we'll just give a very high-level overview on this slide, and then a couple of details for some of the submodules that are being used in these really complex systems. Basically, we'll have usually a source language. Let's call that F for now and say it's French. And we have a target language, such as English. And in general, we'll try to find the highest scoring translation in English based on the posterior that basically conditions on the French input. So this is the only, maybe fortunately or unfortunately, depending on who you ask, the only time we use Bayes' rule in this class. But basically here we want to maximize E for the posterior of E given F. And if you remember Bayes' rule, posterior is just equal to the likelihood times the prior divided by the evidence. The evidence in our case is just P of F, which is the original source sentence in French, and that's fixed, so we can ignore it. And basically, these traditional machine learning traditional sort of machine translation systems will factorize this first. So first, they will try to find a probability here for a French sentence given the current, given in a potential English one. And so we'll basically have 3 major modules in these MT systems. The first one is a translation model, which is basically trained on a parallel corpus. Again, we have a sentence in English, a sentence in French, and we have lots of those examples. And the second one is a language model that is essentially trained on only English. And those language models we're by now quite familiar with. We can train them on arbitrarily sized corpora. Really, we just need an English monolingual corpus. So we can take all of Wikipedia, all news sentences, articles, everything we could find in the English language will help us improve our P of E, our language model here. And the way this basically works is you have some French sentence, and we'll go a little bit more into details here, but on a high level, you have some French sentence. Now your translation model will sort of chop it up into words and phrases, and then try to find which of these words and phrases it has seen in their parallel corpora, and then try to essentially put these together. So you have here kind of pieces of English or broken English. It's just, this phrase I've seen a lot with this other phrase, so let's just translate this. And then we'll have lots of candidates here, and the language model will then help us sort of rescore them and say, well, if I say I, cat, have, then, a, then it wouldn't be a very reasonable English sentence. And so you basically take these two models and you put them together, and the decoder will essentially be a large search that tries to go through all the potential translations that you have and basically scores them. And the output of that will then be proper English. So let's look into the very first step of the translation model, which is alignment. So the goal here is to know which word or phrase in the source language would actually translate to some word or phrase in the target language. And the main message here is that very first step is already very hard. And if you took CS224N, from where we have this example, you will remember that you could basically have an entire lecture just on this first step of the alignment between two different corpora. And so to give you a little bit of a sense and some background on NLP here in the class, we'll go through a couple of examples that show you how hard this is. So the first thing is here our English is on the left side, and here French is on the right side. And the sentence Japan shaken by two new quakes, basically Japan here translates into le Japon. And so we have here a spurious word that actually doesn't have a translation, and now the alignment model has to figure out when to potentially ignore the fact that there's another word in the other language, right? And there's some uncertainty around that. Now it goes the other way too, which says you might have some zero fertility words, or words that aren't translated at all. So if you have, and the program has been implemented in English, and in French you have le programme a été mis en application, then basically here you have, and was just not translated in your parallel corpus. And you also have potentially one-to-many alignments. So implemented in French is basically made into an application in this translation here. So now you have to understand and basically search through the possibilities, and obviously there are many of them, right? This word can now, you don't have to just look at whether this word matches well with one of these, but potentially with any n-gram in this other phrase. And this again is also a simple language. English and French is actually a quite simple kind of language pair, because oftentimes the word order is roughly similar. Not always, but in many cases. And so now imagine you have a word order, a language with a different word order where you actually have to flip almost everything. So now you don't just have to look for this one implemented word about the single word and n-grams at the end of that sentence, but potentially all over that sentence, and try to find which sort of statistically match up really well. And it doesn't end there. The same thing is also true for the other direction. So you have many to one alignments, and those pose problems. And in the end, you can also have many to many alignments. So the poor don't have any money, les pauvres sont démunis. Basically here, don't have any money, or not having any money, basically translates to sont démunis. And so now, basically, that first alignment step will already pose quite a challenging problem, and there are lots of different machine learning models that try to solve that. And unfortunately, and this is the main point here that I make a couple of times, is that this alignment model, as we train it, is not actually, we don't train that to do the final translation. We have here a separate machine learning model that tries to match which words and phrases go together in the different languages. And we maximize this model somehow, yet that maximization is not the final maximization that we actually want to do, which is to produce the real output, right? So you have here so-called pipeline machine learning model, where you train one model here, train another one, train another one. In the end, you kind of put them all together. And that is never quite optimal, because now if you change one, you have no idea how that affects, the other ones and how they interplay. Yes?
So you mentioned that these parallel corpora are aligned, so then don't they contain like aligned word pairs also? Or?
Unfortunately, in most cases, they don't. So the question is, why not align exactly the word pairs and phrase pairs and so on? The main reason there is that you could, and I think there are some tiny corpora where linguists actually sat down and translators and did that. However, you want to have as large of a corpus as possible. And in the end, most of the ones like the European Parliament, the Canadian Parliament, the United Nations, and so on, they're not in the business of translation, right? They just want to translate this as quickly as possible, so they're not asking all their translators to say exactly why they translated each sentence from the other language.
So are they aligned at all, or in some granularity, say a sentence?
Yes, yeah. Sentence or paragraph level is the most common one. Yeah. And in some ways, there had been a revolution in machine translation, and there's some mean quotes about linguists, such as whenever I fire linguists, my accuracy in translation goes up and things like that. Basically, in the beginning, the statistical methods here were the revolution in some sense, because they try to not manually say, all right, whenever I see exactly don't have any money, I will translate it to Sont démunis, right? Like in the very beginning, the systems were rule-based. And then some people took the Bible, for instance, which is translated in almost all languages, and just looked at the statistics, and that gave a huge improvement. And I think we're literally living through the time right now where we see those kinds of improvements and that kind of quick sort of overtaking using deep learning, and that's why we don't spend that much time on these traditional systems, and we'll spend most of the time on deep learning, and hence this lecture. So basically, let's assume we have a way for each single word or phrase we find potentially good phrases. Then basically, that in itself is a huge problem, right? Because now you could look at phrases, you could look at this entire syntactic structure of the sentence. You may try to translate longer and longer phrases. If you see, to be or not to be, right, that's a longer phrase, and maybe you see that in sein oder nicht sein in German, and now you can just translate that entire phrase instead of translating the single words. And so basically, you also need to, at the end of the day, consider all the potential reorderings. And so here in German, if you have geht ja nicht nach Hause, then ja nicht is actually sort of yes not, but in this translation and commonly in parallel corpora, it would just translate to does not. And so he does not go home basically needs to have some reordering. And so just to give you a tiny glimpse of the complexity here of the final step, we look at the final decoder here, which is basically trying to find the best possible translation after knowing that, for instance, here could translate to he, it, or comma he, right? And like I said, ja nicht could translate to yes not if you just look at the single words, but oftentimes you could also say, well, maybe those together translate to does not, and if you have multiple people, to do not, and so on. So now you have all these potential translations. And nach Hause is an interesting one too. Hause could be house or home, or even chamber, or just at home, and then but there are multiple combinations. And so what you have to do in the end is solve a gigantic search problem. And use things like A-star search and other things you may have learned about in an introduction to AI, I think CS221, where you basically have a very long beam search and you try to find, given that I decided that it was he, what would be the most reasonable next phrase that we add after that. And this is also where your language model comes in, because your language model will help you score reasonable next words. All right, so that was a ridiculously short summary of traditional machine translation systems. Again, we could have an entire lecture on that. There are literally hundreds of important details in, all these various steps, and I only really showed two of those steps. The main message here is that there's a lot of human feature engineering going on in these. They're still statistical, they're still trying to compute corpus statistics, but there's still a lot of human feature engineering, and these are very complex systems. And the main problem is that various subsystems of these overall pipelines solve different independent machine learning problems. So you have one optimization problem that solves alignment, another one that solves maybe finding reasonable phrases, another one that extracts features and scores them in a decoder, another one that helps you do reordering, and so on. And they're optimizing their own objective functions and not necessarily the final objective function that you care about. And so maybe the question here is deep learning to the rescue, but it's actually not as obvious yet. Basically, we'll look at the final table of one very recent popular paper that doesn't yet outperform the best system that comes from traditional models. However, when you sort of look into it and you realize here there are 3 authors who have never worked in machine translation. They've worked in computer vision before and in general deep learning. And now after 1 year of work, they get to 0.5% accuracy below a system that has decades of research put into it by thousands of really smart people. And you sort of plot it, you can very easily extrapolate and think that very soon deep learning systems will overtake. I'm fairly confident that if we give this lecture next year, this question mark will be gone. But again, I'm mildly biased. I'm in this field. So the question is, how would we do it? The simplest and cleanest solution here could be if we again have an encoder and decoder, but both are just a single, simple, recurrent neural network. So we have, single word vectors here for each of the languages. We can train, things like word2vec on different languages, right? We've so far only trained it on English, but we could train it on French or German or whatnot. And so here we have, Ich dicke Kiste, German, and maybe we just translate it to awesome sauce in English by basically taking each word here into a recurrent neural network and then basically taking this vector and from this vector immediately translate this. And these here would all just be logistic regression, our softmax layer that we have for other language models, but this time we don't just try to predict the next word, we actually try to predict the sequence of words that come conditioned on that hidden vector. So again, this is kind of crazy when you think about it, right? We're asking here for one vector, one fixed sized vector, to help us translate variable length structures, right? The sentences can be anywhere between 1 to 3 words up to 40 or 50 words. And every time we're asking it, squeeze whatever you have here into these n dimensions. So if at all, these n should be very, very large here, right? If this was at all possible. So this would be sort of the simplest kind of model we could think of. And here we introduce some slight notation for the next couple of slides to simplify things. Whenever I write phi of some inputs, basically every one of these inputs will have a linear transformation matrix associated with it, and we just sum them up. And so the simplest model here would literally be our encoder is a recurrent neural network, and our decoder is that same recurrent neural network. And we just, at every time step, we predict a word that we want to output, and then we just say, well, let's take the maximum word here and say that is the actual translation. And we would just minimize the cross-entropy error for all the target words conditioned on the source words. However, it's not quite that simple. This is a hard problem, and if that worked, then that would have been somewhat surprising given how complex machine translation is, right? Even humans, you ask for any non-trivial sentence, you ask 2 human translators, they wouldn't agree on what it is. So it is kind of asking a lot to have a couple of simple linear transformation matrices followed by a single nonlinearity to capture all the complexity of different kinds of language pairs and how you would translate them. So the rest of the lecture we essentially will spend on various different extensions to that baseline model, and they will get a little gnarly. They'll be at some point very complex, and you really appreciate understanding, having understood your basic Lego pieces, because while it might take you a long time, the steps to actually derive these models should still be fairly straightforward to you now. Okay, so let's go over 5 extensions. Some are relatively simple. The 5th one is going to lead us to these gated recurrent units and LSTMs and a little more complex. So the first one is that we'll basically train different recurrent neural network weights for encoding and decoding, right? So maybe we have here our German model, an encoder, and then we take the last vector here, and then we condition our English decoder on that vector. And now that decoder, for instance, could also be pre-trained as a language model, so it would just, in general, predict reasonable English phrases, even if it wasn't conditioned on anything. But if your corpora, your parallel corpora are large enough, you don't necessarily have to do that. Okay, so this is the first extension. Does that make sense? So when I just, here I kind of quickly just say this is a different color, and so what I mean by that is we have a different WHH here for source and target, or a different phi function. Does that make sense so far? Great. So the next extension, again here we define our phi, and we contrast this to our simple decoder. The next extension is that we'll actually compute every hidden state in the decoder using 3 different inputs. The first one is the previous hidden state. That's the same as what we had before in a standard recurrent neural net. But then we will also actually condition every single step on the last hidden vector of the encoder. So we have here our encoder. We have usually here our HT, and now we'll just define HT at the end of the source sentence as C, and now C will just get its own linear transformation matrix and is added to these other 2. And the other one, and this one is very interesting, is we will actually also make it dependent on the last or the previous predicted output word yt minus 1. So here we'll have a 1 of t encoding. It's a very large matrix, size of our vocabulary, and basically we can modify our decoder hidden state at each time step t based on which word we just predicted, and that will allow the model to not translate the same word over and over again, right? It'll actually tell the model that it's already just translated that word, and it can move on to a different word. So this is the original figure in a paper that essentially introduced this by Cho et al. As a PhD student, Yoshua Benju's group from last year, and this is again one of those kinds of plots. And just to allow you to go and read the literature and not be confused when you see different plots, this is showing the exact same model, just in a different way. And so here they basically make very explicit that we have this 1 of k encoding. This is basically just us retrieving a specific word vector. So here our word representations, they call them S instead of X, but these kinds of word representations are the same. H is also the same. We just basically have here our recurrent neural network model, the same that we've had before. But now we take this vector, the final hidden state here, and now we condition this on all the different time steps Zi here. And we also, for each new computation, take into consideration the previous sampled word. So again, these 2 are exactly the same. They're just different illustrations of the same model. All right, so the next 3 extensions are quick to explain. Basically, instead of just having a single recurrent neural network, we will stack them. We'll make them deeper. That, in many cases, helps, especially if you have a lot of data, and especially if it's a complex problem. And we may actually also train a bidirectional encoder. And then we could, instead of taking just the last vector here, we could take the last and the first from the opposite direction and then condition on that. That certainly helps, because now if you try to predict the next word here, you can actually try to condition it also on this one here, and then that is a much easier translation, because if the languages are both well aligned, so the first couple of words like la croissance économique, economic growth here, those two are more likely to be the same or be well aligned in English, French, and so it's easier if we had a bidirectional recurrent autoencoder that takes sort of the context at the very end and at the very beginning. And similarly, another alternative to having a bidirectional encoder is, and this is an interesting hack that was introduced by a paper that uses LSTMs, we'll cover it later in the lecture, basically to train the input sequence in a reverse order to make a simpler optimization problem. So instead of translating the German Echte Kiste, ABC, to awesome sauce XY in English, we'll actually just try to do the opposite, and we have CBA and try to translate that to XY. What does that gain us? Well, oftentimes for simple language pairs such as English-French, they're well aligned, and so C is more likely to be translated to Y. And now this is basically a deep recurrent neural network, and despite all the various tricks that we'll introduce here for dealing with vanishing gradient problems and such, it is still a much easier problem if your output is here and the input that determines that output is close to the network. And so, close to the actual error messages that you get. And so, because X is more likely to be translated from words in the beginning of the sentence, we just reverse the order here. It's kind of a clever hack, not more, not less. So just reversing the input sequence. All right, the main improvements here and sort of the interesting research that is happening right now is in better units, different ways to compute our hidden activations H. And one that is very interesting, I think, and has a good shot at being used a lot in the future are so-called gated recurrent units. Again, we add this paper in our suggested reading list, and I think some people complain that there's a lot to read in those suggested reading lists, and that is true. This is not a required reading list. It's just if you actually want to learn about all the details of the experiments and the various tricks of the model and so on. We can't really cover all of them all the time. Then this is a good paper to read. The main ideas of gated recurrent units is that we basically want to keep around certain memories, certain elements of the hidden vector to capture long distance dependencies. So we don't want to have a inner product here, so the matrix multiplication. This basically does change our hidden state entirely, right? Every hidden state you will make a huge change to H. And that change depends on all the other elements of H, right? And so instead of doing that, these gated recurrent units want to allow you to keep some elements of your H somewhat constant so you can carry over long distance kinds of information. And that those two go hand in hand, which is basically that will then allow you to have error messages flowing at different strengths. Sometimes your error message changes entirely what each unit does in your hidden state, and other times it will basically just go through the network to maybe even 50 time steps away. So let's define gated recurrent units. Hopefully you will see that really there's only one new little Lego piece here that we add, but everything else is fairly standard. We just put it together in new ways. So the standard recurrent neural network basically computed our hidden layer at the next time step directly with this equation. And now the GRU actually has multiple steps and in some ways multiple little recurrent units inside in order to compute that final H. And the first two steps inside the GRU are to compute two different types of gates. The first one is called an update gate. And really a gate is just another layer. However, instead of using any random nonlinearity, they always use the sigmoid function. Basically, the gates can be kind of seen, as a gate. They can be on or off, open or closed. And if they're on, they will have a certain effect. If they're off, they have a different effect. And so our first gate we'll call an update gate Z, which is basically also just dependent on the current input vector. They all are. And the hidden gate that, the hidden vector, that shouldn't be gate. Let's change that right away. The hidden state of the previous time step. And the reset gate will be computed similarly, but with different weights. So here we have our superscript again, and basically our update gate will use WZ and UZ, and our reset gate will use WR and UR. But the inputs to both of those are the same. Okay, so far so standard, just two types of neural network layers with standard matrices. But note here that ZT and RT do not depend on ZT-1 or RT-1 respectively, but only on the word and the hidden state. And we don't yet know how to compute that hidden state from the previous time step. So let's define that. The next step is to have a new or intermediate or temporary memory content. And that memory content adds the first novel thing, which is this element-wise product here. This is, again, the same Hadamard product or element-wise multiplication. Basically here, we would have, without this R, HT would be basically exactly the same as these two in terms of how it's computed. Just, again, the word vector is one input, and the previous hidden state is another one. But now the reset gate basically allows you to potentially ignore the previous memory entirely and only store information that comes from the word vector. So if R, and again, R here is a vector, so these are all vectors, right? So if the ith element of the current reset gate at time step t, if the ith element here is 0, it basically doesn't matter what your past had said. You will just ignore it entirely. So imagine you were training a sentiment classifier and you say awesome. And then you have a bunch of other words that don't really matter, a bunch of content words. The movie, the actors, everything was awesome, right? Or awesome were all the following things. And now you basically don't want to update that this unit now considers this thing to be positive, right? You basically just update a bunch of content words. This kind of model could now learn to say, well, if it's this kind of word from this part of the vector space, I will just ignore it. And I will basically just take into consideration what this current input gives me. And now the final memory at the time step basically combines the current and the previous time steps. So ZT here is our update gate. And if the ith element here of ZT is 1, we basically just copy over the previous hidden state. And we ignore what currently happened entirely. So that entire word, all of that, basically ignore it. If the opposite is true, ZT is 0, then we basically take this entire one, and then we can look at either the word or a word and its connection to previous memories. Yes?
So RT is low in general for words that have a direct translation that pretty much always works? Because then we don't care about the previous what came before. Like if there's a direct translation between a German and an English word that always works, then we don't need to, or the model doesn't need to take as input what happened before.
Right. So the question is, how does R relate to for machine translation? And unfortunately, the story isn't quite that simple. So one, these reset gates, you have one for every single unit of all the words, right? So RT and ZT here are vectors, and so if you have 300-dimensional word vectors or 300-dimensional hidden representation, then each of the units can decide by itself. So you might want to keep around some dimensions of that word, so it knows it's about politics or something, and adds other words that are about politics and gives a higher probability to those. It's not really that gate is turned on or off for the entirety of the word. And the other thing, the other complexity is you'll actually eventually stack them, and then a lot of those intuitions break down even more. So I wish there was a nice sort of, here's a visualization, and this is exactly what this ith unit of the R vector does, but it's not that simple. Basically, the intuition is more sort of on a high level that you can reset previous inputs in a specific way for some of the units. So yeah, I'll give some more intuition in the next in the next slide. Here's my attempt at a clean illustration. I am not really happy with any of the illustrations that are out there in the original papers, but honestly, I don't think this is the best one either. I don't think there's a super nice, clean way to visualize this. But at least, you know, here's one attempt. So to understand these, each of these is basically a vector. So here we have our word vectors, and now we basically compute our two gates, the reset gate and the update gate. And now we look here at the memory that has been reset, and note how all these four don't depend on the previous time steps themselves, but only indirectly based on the final memory output. And whenever we have a multiplication here, an element-wise multiplication, I have these kinds of dotted lines here that are straight, and they basically modify it. So zt here modifies how ht is computed from ht minus 1 and h tilde at time step t, and the reset gate modifies how h tilde t is computed given this input and the word vectors. But RT here, note how RT does not actually modify W of xt. Yes?
So you no longer have the matrices WHH and WXH. And, like you do not have the matrix multiplication of fixed state with the next state. Like in the simple algorithm, we do something like ht minus 1 equal to some function of WHH times ht equal to some function of WHH times ht with t minus 1. So we no longer have those matrices.
In some ways, that WHH can be seen as this U here, right? But now this U won't necessarily have the power to change given the previous time step unless the reset gate agrees with that. So the reset gate allows you to basically take into consideration your previous time step. And similarly, and there's some interesting interactions here too, right? If zt is just entirely, every element of zt is 1, then basically what you're telling your model is ignore the entire input at this time step and just copy over your previous hidden state. And that kind of copying over basically has your gradient, your delta, your error messages that you compute during backpropagation don't get smaller and smaller, right? They just get continuously sent back through the network. So this kind of model has some chance at doing things like counting. You would think, oh man, recurrent neural networks are so powerful, but it turns out a simple standard recurrent neural network can't even count. It cannot like give as an output, or at least it's very, very hard and wouldn't work for very long sequences. Let's say all you want to do, you have sequences of A and B, just two characters A, B. And at the end of the sequence, you want to output whether you had the same numbers of A's and B's or not. So now you could have, you know, A, B, B, and it says yes. You can have A, B, A, B, and it says yes. Or you can have A, B, 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 A, and it should say no at this point. Right? And you can say that at every single time step. Now, a standard recurrent neural network has a hard time with just that task. But here, you can kind of see how some of these memories basically just keep around one counter, and then you keep adding to that counter. At least for LSTMs, which we'll cover in the next two slides, that will be even more intuitive. These kinds of models have a shot at doing that. Yes?
So it seems like the purpose of both RT and ZT is to figure out when we take into account previous information and when we take into account the current input. Is there a specific reason why we need both of them?
Yes, there is. I guess in some ways, if you only had RT here, you would still, in every time step, let's say you didn't have HT tilde, but HT tilde would just like directly compute HT, then at this time step here, you would always take into consideration the word vector somehow. But maybe you want to entirely ignore the word vector. And that's what ZT allows you to do. Basically here, if ZT is all 1, you just copy over your previous time step, and you can ignore the word vector entirely.
If we only have ZT?
If you only have ZT, then you wouldn't have a way to weight how much these two should interact in order to then compute the next memory. Yes?
Is there any reason we can't define ZT to be how much we want to include information from the current word vector and then just switch the 1 minuses around?
Yes, you're totally right. In fact, I read 2 different papers and by the same authors, and in one paper it was ZT times HT minus 1, the other one was 1 minus ZT H minus 1. So also you'll actually notice this in the LSTM. We'll soon have a forget gate, and really it's kind of the not forget gate when you look at the actual equations, but yeah, so be on your feet, think on your feet, yeah.
How important is the 10H?
The 10H is actually, so I don't know if people compared this to ReLUs or not, but in general, this is the standard. So people don't usually use F here and have like try a bunch of different ones. For these two, it definitely has to be sigmoid. The gates can be on or off, between 0 and 1. Really, they're never quite entirely 0, entirely 1. They're a little leaky, right? You have to have very, very large weights to push it to be basically close to 1. But yeah, most units here use 10H. I guess the problem is if you have rectified linear units, then maybe this multiplication here won't help you very much, right? So this multiplication is between 0 and 1. But now if you have 1,000 here, and you just multiply it by 0.7 or 0.9, then it might still be a really, really large number. And so the gates have less power to really turn something around or turn something on and off if the ranges are so large.
Okay, so I guess it's still, my question is how nonlinear the gate is. There a billion functions you could put in there.
Yes, and so like you have the soft sign, for instance, or here you have a sigmoid 2. It's just a rectified linear unit, which is the other one that is very popular for recurrent neural networks. That might have trouble because then it can't really scale. But yeah, you're right. So there's the soft sign or the sigmoid function or maybe the hard 10H or other options. Yeah, I don't see, they may have tried it, but they didn't talk about it in the papers, the pros and cons.
Do you have any personal experience with like how carefully you have to initialize and tune these things?
So the initialization from all the projects can be very important, right? Again, if you misinitialize, and it's this idea that I described before, if you initialize it such that your nonlinearities are all maxed out, your gradient is 0, that would be quite bad. And people have played around with some initialization, and it is definitely important, but other than for some gated recurrent units, we have here this initialization hack of the identity matrix. Other people actually define also to try to have orthogonal matrices there. There's some interesting ideas around that. Yeah.
So in this case, we only have like 2 things like X and H, but in the earlier slides you showed that the H also depends on other stuff like the previous output word and like how would this be modified to?
That's a great question. So in many cases, you can just add here a second, plus V times something else. If you have other kinds of inputs. In fact, these things get so complicated that the most popular way to, in the end, describe these kinds of models, it's just saying like, GRU, you have some X, you get some H out. So, and now you can stack them and you can put them together in various crazy ways. So we'll get to that for LSTMs. All right, so I think we covered, thanks to your great questions, most of these intuitions. But let's just reiterate if we did. So if the reset gates here are close to 0, these guys, we can ignore the previous hidden state entirely for H tilde, and that basically allows the model to drop information that is irrelevant in the future. I think we said this also. The update gate Z controls basically how much of the past state should matter at the current time step. And so if Z is close to 1, then we can basically copy over the information here in that unit through many, many time steps. So imagine there's also basically people who worked with recurrent neural networks and they didn't have large enough data sets to really train them, created a lot of interesting synthetic examples to show, oh, look, the standard recurrent neural network totally fails on this very simple problem. There's another one that can kind of be described the following way. Imagine I gave you, in the next couple of sentences, 2 numbers, and I want at the end of those sentences the sum of those 2 numbers, right? So first I say 2, and now I distract you with a bunch of other stuff that has nothing to do with the question I just asked, and now I say 3, and now I ask you what the sum is, right? And now, basically, given what I just told you in the beginning, you really only had to pay attention to 2 and 3, right, to give the final answer. But if you only had these kinds of equations here, 2 and 3 would be totally drawn out, and the hidden state could not capture that anymore. But here, you know, given what kinds of things you backpropagate into these hidden states, they could really, you know, if you have enough training examples, could show you, oh, only if you see a word vector that is a number should you now allow this to modify your hidden state. And so a lot of these kinds of synthetic problems are close to impossible to do with standard recurrent neural networks. Yes?
Just another question about the intuition behind these gates. So, like, is there sort of an intuitive reason why you couldn't? I mean, so essentially what you're doing with the gates is like computing like an attenuation for a particular signal.
Mm-hmm.
So is there any reason why those attenuations couldn't be happening on the same level rather than like one inside of a KNH and one like at the next level up? So like you just say, how much do I want to attenuate this one and how much do I want to attenuate this one? And then maybe normalize them so they're equal to, so they sum to 1 or something.
So I guess the question is like, why have the RT inside here, inside the 10H, and not maybe outside the 10H? The main point here is that once something is inside the 10H, you allow for some nonlinear interactions between the two things. Once it's outside, then the inside is just, again, a linear transformation. You sum up these two things, and then you apply the nonlinearity. So it's kind of similar to having multiple layers, right? You could, at the very end, change an output, but if you change it inside, then you allow for nonlinear interactions. So that is one answer. Another also reasonable one is maybe you're right. Maybe this would work better. So I think this is, this is a paper from last year. It's very fresh. And I'm very certain that we'll see a lot of modifications. In fact, the LSTMs, who have been around for almost 2 decades, there's so many papers that the original authors just a couple of weeks ago published a paper calling LSTMs a Search Space Odyssey, and basically compared like 20 different variants of LSTMs, where somebody was like, oh, but what if I have another, V vector here that I do an inner product with, right? And so like, there are lots of modifications, and unfortunately, you really have to try to gain intuitions, try to visualize what's going on if you want to come up with models that aren't just different, but are actually provably a lot better. One nice intuition here that the authors did mention in their paper, and which I think is intuitive, is that the units basically allow you to have some short-term dependencies based on reset gates being very active, right? If your reset gates are very active, let's say half of your reset gates are very active, then that first half of your hidden state will continuously update based on what's going on every time, where the other ones are almost always 0, then you kind of don't take that into consideration as much. Here's one illustration that is more commonly seen, and this is one from that paper. However, I don't think it's that great. I mean, you can kind of see, okay, here's your gate. It can turn on and off. This is, I guess, for just a single element of that vector, and then depending on that, your H can modify your H tilde can modify your H. So this is kind of what we have here. Your H tilde can modify your next HT based on these two. So, but it's, I don't know, they're missing a lot. And then it's not clear here if you just keep on going in circles and where it goes out and so on. I'm not a big fan of this particular way to illustrate them, but you'll see this in the literature too. So basically the only new Lego piece that we had here was this element-wise multiplication. And so if you were to try to derive this now, and again, I don't think it's too hard to try to derive this. Let's say you have just 2 hidden units, 2 time steps, and look at your gates and see how they turn on and off, and try to write that all out in all the gory details. But basically here, the only thing that's different is we have another function inside. Instead of just being a linear function, we have here multiplication, and we all hopefully know the derivative of one element of simple multiplication. The other one is basically a constant for that derivative, so it's fairly straightforward. And so the rest here is a similar kind of chain rule. But imagine you will stack these kinds of gated recurrent units. So now at every computation of H, you actually have a lot of other inside computation. If you actually try to write all that out in all its gory details, it's very challenging. And so what you usually do when you implement these kinds of models is you will have one class, and that class is a GRU class. And now that class takes as input during forward, that has 2 functions, right? A forward function, forward propagation function, and a backwards propagation function. The forward one takes as input some things. In this case, probably only xt and ht minus 1. And then you do all your math, you upgrade, you compute everything, and you give an output for forward propagation, which is ht minus 1. And you keep around stuff inside that class to compute internal values, such as your gates. And then you have a backprop function that takes as input a delta vector, the errors that you've gotten from the previous layer. And we've computed, we had one nice function in our previous lecture. What is the delta that goes down from this layer? And now the backwards function will just take in a delta, compute a bunch of stuff, give you a bunch of gradients that you get for this unit, and then output another delta that you send to the next lower layer. And this is the way you have to implement these if you want to be able to sort of quickly build them and put together new kinds of units. Even for just the recurrent ones, right, you can't actually write out for every single length, right? You have to implement this in some kind of modularized way. For those of you who are, even after all the pain from the p-sets, still really don't like to take these derivatives by hand, you can use systems like Python's Theano, which allows you to simply update, basically define your model exactly this way. You just define the forward propagation, and unlike with graphical models, where once you know the definition of your generation procedure, you still have tons of work, and it's unclear how to do actual inference. Once you know this forward propagation, right, everything else is deterministic. And if you write it and use Theano, it will basically give you automatic differentiation and just compute the gradients analytically for you, and then you can update your models. And you will know why this is important once we look at this slide, which defines the LSTMs. And so the slide after that will try to show you some illustrations, which again are going to be even worse than for the GRU. So let's walk a little bit through the intuitions of an LSTM. And again, most people in the end will just write, this is an LSTM, and not care that much about the internals. So we have basically now 3 different kinds of gates. So we have an input gate that basically will be very high if the current cell, the current input actually matters, and you want it to really update. And so basically this is again just the same kind of idea here that we had in GRU. You take as input, all of these take as input the current word vector x, and the previous time step ht minus 1. Right? So in this sense, fairly straightforward, 4 different types of layers. And again, it's just important to note here that none of the input, forget gates, and so on depend on the previous input or forget gates, but only on the previous state of what we now call the hidden state H, or we often now call it the memory. Okay, so now we have an input gate. We also have a forget gate. So maybe I just want to tell you right now, reset and forget what I just told you. So you could create simple problems in both machine translation or totally synthetic examples where I explicitly tell you to ignore the previous numbers that I just told you and only sum what comes after this sentence. And so the forget gates basically allow you to explicitly ignore what you have just learned until now. The interesting thing here, this is the sort of a new kind of gate that really didn't exist in the GRU, is you also have an output gate. The output gate will essentially allow you to not tell the rest of the network what your internal state actually is. So you could compute a bunch of stuff, you could remember things, but just not blur them out. Not tell the rest of the network what's going on. Just keep them around. And so usually this will depend on like if you want to actually predict a word, for instance, maybe you want to wait until you see the entire sequence and then you want to output only something. And so you basically want to force the model to not actually give the output of its hidden state or hidden memory. All right, so then this is somewhat similar to the GRU as well. And again, we're not historical here, right? This model is from '97. The GRU is from last year. But I think sort of the pedagogy is better to go the other way around. OK, so the new memory cell here is also, again, a 10H unit. And we have here same kind of linear transformations and so on. So now the main novelty here is how do we actually put all these gates together? And it's fairly straightforward in some ways, right? We just have two element-wise multiplications. And we, again, either care about our previous memory CT-1 or about the thing that we just computed at our current time step. And then we add those two, and then we apply an element-wise nonlinearity again. And now, before we actually output the HT, note here how CT actually has access to its own memories, right? So it doesn't have to look at HT as much, but of course HT will depend, make all the next gates. It has a lot of impact on the next couple of gates. Yeah, that's the LSTM for you. Are there any questions so far? Yes.
So just the new memory cell. So it's, I guess more so the output, like how much of the cell is exposed.
Mm-hmm.
What does it mean to have, if there's a lot of information that's only exposed internally and not a lot exposed externally? Do you give an intuition for what that would amount to in terms of why we would want that kind of thing?
So one example, for instance, would be I want you to take into consideration a couple of facts and then reason over those facts and then give me an output. So maybe I ask, and these are kinds of interesting things that we may get to with question answering and towards the very end of this class. Imagine I tell you at any given point you might want to tell me where is the toy, and now I tell you John picked up the toy, and now you shouldn't actually say anything because you don't know yet where the toy is, right? And now the next sentence is John walked to the kitchen, and now you should say output question where's the toy. Now you should put output kitchen, right? And so this is kind of I could have come up with more examples where I keep not telling you where John actually is. You just know that the toy is with John, and you don't want to actually output anything. That is sort of one very NLP kind of intuition. Of course, there are lots of other kinds of tasks, and I actually have never seen a really great visualization that shows that that's really what's going on, right? Like you have 300-dimensional kinds of vectors, and it's unclear whether each of these will really do and exactly forget a specific fact or something, especially for NLP. I think a lot of the intuition here comes from the math, which is if you want to be able to keep track, you want to have a counter for this simple synthetic problem I just described earlier, where I give you A's and B's, and I want you at some point to say yes if I gave you exactly the same numbers of A's and B's, or no if they're slightly different. So I could give you 100,000 A's, and now for the next 99,999 steps, you should be able to say no, 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 which means you basically now have to have a tracker around. But maybe I don't ask you to output it every time. Maybe I only at the very end tell you yes or no. And now you have to keep this tracker around at every time step without actually giving it as output. Yeah.
Why 10H for the memory cell?
Again, you could have like different kinds of nonlinearities, but I think the same intuition holds here that if it was a rectified linear unit, which is sort of, in most cases, for most of your models, at the very least, I would ask you to compare 10H and rectified linear. And there are lots of other ones like soft sign that has slightly better gradient around 0, and the hard 10H and so on, which is just the 10H that is more efficient to compute and has really turns off units. But in general, those are sort of our default neural network kinds of models. You know that deep neural networks that use 10H or rectified linear units are general function approximators. So whatever kind of complex function you have, they can approximate that. It is kind of just a default. It is nice because it is basically bounded between -1 and 1, and so the gates really can have a lot of power to get rid of some information or keep it around.
So it's kind of just like a rate of
Yeah, well, you could say that that's what nonlinearities are, but if you didn't have nonlinearities, then you just have linear functions, and then none of these powerful methods would work as well. Yeah.
I was just curious. How long of a dependencies can these things capture?
These can basically keep track of counts, and it's arbitrary. Like you can kind of, and maybe this is one way to gain some intuition. You could kind of try to see what kinds of weights would have to be on and off to do this A/B example. You could probably maybe even come up with ways to set them specifically such that it basically creates a counter and can count at that point.
You just said 10H and their general function approximators. Can you talk a little bit about that?
Boy, yeah. So there's a lot of.
Something. Point to a paper or something.
Yeah, I can. Yeah, so there's some very early neural network papers. Maybe I'll add it to the suggested reading list.
Kind of the reason why neural networks work, because they just can approximate any function.
If they're deep enough and wide enough and so on, or actually even if a one-layer neural network that is wide enough could approximate any function, it just has to be exponentially more wide than it would have to be deep. But yeah, so there's lots of interesting math, and I can add some reading some papers to the reading list. Yeah. Yeah.
When do people use GRUs versus LSTM?
I'll get to that in a little bit. It's the jury is still out. People, the GRUs are only around for a couple months now. So yeah. We'll get to that in 1 or 2 slides. So basically, these illustrations are a bit overwhelming. I don't know how helpful they really are, but you can kind of see here. You have your input gates, you have your memory cells, you have an output gate, and here you have your internal state, and that could, in theory, if your forget gates would never turn on or off, really, depending if you have ft or 1 minus f. Really, they could just keep around that memory forever and have zero vanishing gradient problems. Or if your forget gate wants to, it just kills it and resets it. So yeah, so these are some different ones. I find this one probably the least helpful. This one, the original one here, is a little more helpful. You can kind of see, they tried to say, when do you have a nonlinearity here? And these big black ones are basically your element-wise multiplications. Here you have your CT, which is exactly the guy here that basically keeps just copying or adding the previous one, unless the forget gate messes with that, which is kind of here, that little forget gate here. Here you could also just set the forget gate to 1, and then it cannot forget. That memory will always keep the gradient around. Yeah.
The left one is more powerful than your equations, right? It has more internal, like the red dot connects to the green ones.
So the C, yeah, there are lots of different modifications, and we'll have to really carefully look through how each one here modifies the other. I mean, this one basically just also doesn't show you all the gory details. But yeah, in fact, I think this one here is more standard and sort of the default one that is very, very powerful. There's one paper, and I'll link to that too. It's not that interesting. It's just here are 20 different modifications of turning this thing on, or having an extra parameter here, or taking that parameter out, and so on. And it really tries to, on a couple of data sets, have lots of plots with lots of comparisons. It's called it's by the original author, at least Professor Jürgen Schmidhuber, and I think some of his newer students now. It's called LSTM's A Search Space Odyssey, and the title says a lot. But I think the important intuition here that I do want you all to take away is that these memory cells can basically keep information intact unless the inputs make them forget it or overwrite it in some meaningful way. And again, this boils down to not suffering now as much from the vanishing gradient problem. And I think this is a general interesting approach too. You can try to hammer away on a specific model, and you just say, I want that recurrent neural network, that standard recurrent neural network, to do it better. Because in theory, it should. But in practice, the optimization problem is such that it just can't. Or you can just say, well, I want to have certain long-range dependencies. I want certain things to stick around for longer. Maybe I'll just design a new model that tries to add this intuition, tries to add something here where the gradient wouldn't vanish and things like that. So LSTMs are currently sort of very hip and en vogue, and for most sequence models, I think right now, if you were to try to publish a paper, people would ask you, why didn't you compare to LSTMs? In fact, they're so powerful, they now have been extended also, and Kai Sheng, who's a master's student right now with Chris Manning, and we had submitted a paper just recently where we use LSTMs for different kinds of structures that aren't just recurrent. They're actually recursive, which we'll talk about in the next lecture. But generally, LSTMs are very powerful, especially when stacked. And once you try to stack them, you can basically give up on really trying to write out those models. You will just basically say you have different LSTM layers. You have 1 and 2, and those go. You have your X input here, and this is just your previous H T minus 1, which also came from an LSTM. So you can also stack these units, right? In the end, they are really just, they get some input and they produce some output. Huh. Could you close the door, please? All right, just to give you a brief overview here of how well they work. This is basically maybe this one here is the most interesting one. This is basically a big competition. Sorry, this one up here. And blue points are basically the metric that machine translation researchers use to compare. It is kind of an idea of how many n-grams overlap between your translation and the ground truth translations that you have. And you can combine multiple LSTMs, make them very deep, and so on. And no matter how many things you can do, it'll get you up to a certain performance. In this case, 34.8. However, when you take sort of the best WMT system, which is a competition that is run for many years, that best system is at 37 blue score, and the best sort of deep learning system is only at 36.5. But again, this is done by people who hadn't worked that much in machine translation, and only after 1 year they got a system that does all these different things. There's still lots of things you can fix. Hi.
We have this room reserved from 2:50.
Well, 1 minute. Oh, now 2. Thanks. All right. So basically, it does work very well, but it can still be improved. And one big thing here are word vectors, for instance. They're still very important. We can learn very interesting vectors. You can look at these hidden units from the encoder, and they actually capture interesting passive-active invariances. And maybe we'll summarize here. So basically, recurrent neural networks are very powerful. There's a lot of ongoing work right now. I think gated recurrent units are clearly better than standard recurrent ones, but LSTMs may even still be better. There's juries still out there, actually some papers that compare the two, and sometimes GRUs work better, sometimes LSTMs work better. Again, this was a very advanced lecture, so hopefully you gained some intuitions. I encourage you to explore these a little bit. Don't worry if you don't feel super comfortable deriving all the equations. And the next lecture will actually talk about recursive neural networks that are also powerful but much simpler.